Hello and welcome to another video on physiology. In this video, we are going to talk about the heart conduction system. The first thing we should mention is that in the heart, we distinguish two types of cells. Cells that form the conduction system and cells that form the working myocardium. Conduction system contains cells that generate and conduct electrical impulses, and we're going to talk about these cells in this video. And then the working myocardium is composed of cells that respond to these electrical impulses. And just to refresh our Latin, myocardium means cardiac muscle tissue. When it comes to the anatomical division of the conduction system, there are 5 parts. The first part is the sinoatrial node, also called the primary pacemaker, because it generates electrical impulses. I'll explain why the signal is generated exactly in this part of the heart in a minute. When the sinoatrial node has generated the signal, it is then conducted to the atrioventricular node. From there, it goes to the bundle of His, and then through the left and right bundle branches, which are also sometimes called the Vara branches. The last part are the Purkijne fibres, which further transmit the impulses. The cells of the conduction system are very special in the fact that they don't have a constant resting potential. Before I explain how that works and why, let me just recap 3 very important terms from general physiology: hyperpolarization, depolarization, and repolarization. To explain them, we will graph the membrane potential over time and look at how it can change. Imagine that our cell has a negative membrane potential, let's say minus 50 millivolts. Now, let's say that there's a change in the ions and the membrane potential becomes even more negative. This is called hyperpolarization. If it's the other way around and the membrane potential becomes more positive, then it's called depolarization. And finally, repolarization is when the membrane potential becomes negative again after a depolarization. And then hypothetically, if the membrane potential became more positive, that would be depolarization again, right? Great. So now let's graph the membrane potential of a conduction system cell over time. We will start in somewhere around minus 70 millivolts. What you cannot see in the graph is that an action potential has taken place and the heart has contracted. So we're looking at a membrane potential after an action potential. Now, what will happen is that the cell membrane potential will immediately start to depolarize until it reaches a certain value that we call threshold. When the membrane potential reaches the threshold, another action potential is elicited. And when the action potential is over, the membrane potential depolarizes again, and so on and so on. So that's why the cells of the conduction system don't have a resting membrane potential, because they always spontaneously depolarize. Now let's look at the graph again, but this time we will explain in detail how the action potential is elicited. The first thing that happens is that sodium ions enter the cell, and because they are positively charged, they cause depolarization. When the membrane potential reaches threshold, an action potential is elicited, and positively charged calcium ions enter the cell. At around 10 millivolts, the membrane potential starts to repolarize as potassium ions leave the cell. Because they are positively charged, the membrane potential becomes more and more negative until it reaches the value of around minus 70 millivolts, and the process repeats again. All parts of the conduction system don't have a resting membrane potential and spontaneously depolarize. However, the pacemaker cell is the sinoatrial node. It's because the sinoatrial node has the highest rhythm in which it depolarizes. It's around 60 to 100 a minute. The other bars are a bit slower. However, if theoretically the sinoatrial node wasn't working properly, then the atrioventricular system would be the pacemaker with the frequency of around 40 to 60. One of the most important characteristics of the heart is automaticity. Automaticity means that the heart is able to generate its own impulses. So if hypothetically you took the heart out of the body but provided enough nutrients, it would still contract regularly. However, sometimes you want the heart to behave a bit differently because we're, for example, playing football and need it to contract faster, and this is enabled by cardiac nerves. There are three main substances that help us to modulate heart action, and those are acetylcholine, norepinephrine, and epinephrine. These three substances can change what is known as chronotropism and dromotropism. Chronotropism refers to the rate of impulse generation, and dromotropism to the velocity of impulse conduction. Norepinephrine and epinephrine have a positive chronotropic effect, which means that they stimulate the heart to generate contraction impulses more frequently. They also have a positive dromotropic effect, which simply means that they stimulate faster conduction of the contraction impulse. Simply said, because of norepinephrine and epinephrine, our hearts will beat faster. On the other hand, acetylcholine has the opposite effect, decreasing the rate of impulse generation and also the velocity of impulse conduction. This means that it has a negative chronotropic and dromotropic effect, and as a result, our hearts beat more slowly. Now we will talk about these three substances again, but in more detail, so that you understand why they make the heart beat faster or more slowly. Let's start with epinephrine and norepinephrine. Norepinephrine is released by the sympathetic nerve fibers and epinephrine by plasma. They bind to so-called beta-1 adrenergic receptors, which eventually results in higher permeability of the cell membrane to sodium. We said that when the action potential is over, the cell starts to depolarize because of sodium ions entering the cell. Now, if the cell membrane is more permeable to sodium, the membrane potential can reach the threshold faster, and then the same goes for the action potential. This is important in clinical medicine because if you give your patient the so-called beta blockers, you inhibit the binding of epinephrine and norepinephrine to these receptors, and then the heart beats more slowly, which can help you with hypertension, high blood pressure. Acetylcholine, on the other hand, is released by parasympathetic fibers of the vagus nerve, the 10th cranial nerve. Acetylcholine binds to muskarinic cholineceptors, or M cholineceptors, which results in higher permeability to potassium. Remember when we said that when potassium leaves the cell, the membrane potential repolarizes? Well, if the membrane potential is more permeable to potassium and more potassium leaves, the membrane potential will become even more negative than usual, and then will be much more difficult for the membrane potential to reach threshold. This essentially means that because it will take more time to elicit an action potential, the heart will beat more slowly. Great. So that's it for physiology of the conduction system. I hope this video helped you to understand how the system works and why it is so important. If you like this video, please consider subscribing, as there will be more videos on physiology in the future. Thank you, and until next time, don't forget that medicine can be easy.